Hello, today I'll be presenting on the adaptive immune system, specifically focusing on T cell mediated immunity and B cell mediated immunity. This presentation is based on chapters 60 and 61 of the Levinson's Review of Medical Microbiology and Immunology. Along with the three assigned immunology videos in recent research from 2025, my goal is to clearly explain how these two branches of adaptive immunity work. Not only that, but also how they apply in clinical practice and how are they connected to a broader understanding of health and purpose. To start, let's look at the foundations of adaptive immunity. Introduction. Adaptive immunity is one of the most remarkable systems in the human body. Unlike innate immunity, which responds quickly but non-specifically, adaptive immunity provides highly targeted responses to specific pathogens. It recognizes foreign antigens, generates specialized cells and antibodies, and it also creates long lasting memory. What makes it especially powerful is that it has the ability to become stronger and more efficient with each exposure. Today, we will explore how this system works through T cells and B cells and why each is essential. Now that we set the foundation, let's break off into the two major pathways. Overview of adaptive immunity. Adaptive immunity has two major branches. The first is T cell mediated immunity, which deals with intracellular pathogens such as viruses and some bacteria. The second is B cell mediated or antibody mediated immunity, which primarily targets extracellular pathogens and toxins. Both pathways depend on antigen recognition, expansion, and memory cell formation, even though they operate differently. Let's talk about deeper, oops, excuse me. Let's talk about how much more these T cells are able to operate. T cells and their key concepts based on Levinson on chapter 60. So, T cells originate in the bone marrow but mature in the thymus, where they actually develop specificity for foreign antigens and tolerance to self. According to Levinson, T cells require antigens to be presented to them on MHC molecules, which ensures precision in their activation. The main T cell subsets include CD8 plus cytotic cell T cells and CD4 plus helper T cells and regulatory T cells, each which unique roles which each with unique roles in orchestrating immunity. Now let's explore how these subsets carry out their specialized functions. CD8 plus and CD8 4 plus T cells. CD8 plus cytotoxic T cells identify infected cells through peptides that are displayed on MHC class 1 molecules. Once activated, they kill infected cells using pathways such as porphin, Ganzyme, and FAS-L. CD4 plus helper T cells, on the other hand, recognize antigen presented on MHC class 2 and release cytokines that activate macrophages, support B cells, and enhance inflammation. These helper T cells essentially act as coordinators for the immune system response. To better visualize these mechanisms, let's take a look at what this first video had all entailed and what it had covered. So the first video that I had pulled was the immunology map, and this one shows how the infected cells display abnormal peptides on MHC1, which CD8 plus T cells detect like inspectors, which are used, like in this video, as ID badges. Once activated, T cells expand, and they are expanded into thousands of identical effector cells. And the concept here is called um, clonal ex- clon- clonal expansion. This is central and based on chapter 60, and it's also talked about. So this video basically just demonstrates the killing mechanisms in the porphyrin forms, which has pores, and the pores become infected within the cell membrane. This causes apoptosis. And this aligns perfectly with the textbook because the explanation within the text says that it provides um, the T cells, which are going to be indispensable for clearing viral infections. So now that we've covered that, let's look into how the T cell branch um, it actually is in action. And now we need to shift over into the B cells. B cell activation. In chapter 61, Levinson explains that B cells recognize antigens and they're directly going to be recognized through their B cell receptor. However, full activation usually requires help from CD4 plus T cells. When activated, B cells differentiate into plasma cells that secrete antibodies and memory B cells that provide faster immunity during future exposures. Helper T cells provide signals like CD40L and cytokines, which are essentially going to be used for class switch recombination. Let's look more closely at the key antibody functions that result from this process. Antibody actions. Antibodies are used to protect, and it's used to protect in several different ways. They can neutralize viruses, toxins, and it's also used to allow them to engulf easier. And it's also used to activate the complement system to destroy bacteria. Through class switching, the B cells change from producing IgM to more specialized antibodies such as IgG, IgA, or IgE. Depending on the infection type, the cytokine signals. This also will allow a humoral response to be highly adaptive and tailored. So the next video kind of ties into that as well, and it talks about the T cell and B cell branches. So the video for this one is the immunology map, and it gives us more of a combined overview of adaptive immunity. It illustrates antigen presentation, helper T cell activation, B cell differentiation, and it shows how the arms of communication depend on one another. The animation also highlights memory formation. Both memory T cells and B cells remain in the in the body long term. That said, I guess I would say that it enables more of a faster and stronger responses with future exposures. The the visual the visual mirrors Levinson's explanation that the adaptive immunity improves with time and experience. So now that that's covered, let's go ahead and kind of just apply our knowledge and incorporate some things that are real world clinical examples. So, for the first one, I wanted to talk about a case study that I have found that kind of um, it just centers itself on T cell dysfunction. So, in the first case, a patient has difficulty clearing a viral infection. Lab results show reduced CD8 plus T cell activity. According to Levinson, impaired cytotoxic T cell functions directly leads to prolonged viral shedding and recurrent infections. This case illustrates how essential CD8 plus cells are used for combating intracellular pathogens. Without them, the body cannot effectively eliminate infected host cells. So that gives us more of an insight as to how the T cell is being utilized within the body and how it's used to combat within the immune system. So next, we're going to explore a case study that's involving the B cell and the antibody deficiencies. So case study two. Case study two is a B cell dysfunction. So in this case, a child experiences reoccurring bacterial infections and low IgG and IgA levels. The findings are consistent with a deficit of, well, it's consistent with the defect in a class switch recombination. As Levinson had explained in our text, these patients can produce IgM but cannot switch to the more specialized antibodies needed for mucosal defense and long term immunity. And this case demonstrates how critical B cells and antibodies are used for protection against extracellular pathogens. And after reviewing these case studies, I just want to go ahead and swing over to the recent discoveries and talk about how the immune um, system and immune memory evolves. And this is a recent study that I had researched and found. This is a research update and it also has implications. So, a 2025 study by Hong Wang, excuse me, and colleagues found that memory B cells continue evolving for more than a year after a viral infection. Their antibodies become more diverse and higher affinity over time. This discovery raises important questions about booster timing, long term immunity, and how vaccines should be scheduled. It also highlights ongoing controversies such as long term immunity, how long does it really truly last, and whether or not boosting too early might interrupt natural B cell um, maturation. So that being said, it's more like a policy thing, just trying to see if it's better to do the boost at a certain time frame rather than doing a boost, um, during the time that the B cell is um, within maturation. So finally, let's just go ahead and reflect on a large significant part of this presentation, which is our faith, integration, and the conclusion. As I studied these immune mechanisms, I was reminded of how scripture describes the body as fearfully and wonderfully made, which is in Psalms 139:14. Um, the precision of T cell selection and the adaptability of antibodies and the formation of memory all point to an intentional and purposeful design. Just as the immune system protects the body, we are called to protect and serve one another in love, as described in Galatians 5, verse 13. In conclusion, adaptive immunity is a dynamic, highly coordinated system that enables long term protection. Understanding T cell and B cell mechanisms not only supports clinical practice, but it also deepens our appreciation for the complexity and resilience of the human body. That said, this concludes my presentation, and thank you for listening.